Hi everyone, please join me as I light up your life with some LED fun where I will be investigating the intrinsic and active band gap energies of different semiconductors, as well as their dependence on temperature and molecular makeup. So, an LED diode is a light-emitting semiconductor capable of releasing photons of different energies when a voltage is applied onto the semiconductor die composed of metallic alloy. Essentially, the electrons within its semiconductor are effectively excited into a higher energy state and undergo photorelaxation, releasing energy in the form of photons across the visible light spectrum as a function of what is known as the active band gap energy. So, how does this work? As mentioned before, an LED diode emits light once a voltage is applied to its semiconductor composed of a metal alloy. To understand how this occurs, we need to look at what's going on at the atomic scale. When metal atoms are supplied with potential energy in the form of voltage, an excitation of its electrons will occur from its valence orbital to that of an unoccupied higher energy orbital. As you increase the number of metal atoms, the respective orbitals will begin to overlap, allowing bonds to form. This formation of bonds will then cause a delocalization of the energy levels within the valence orbitals of the metal atoms, and consequently, their vacant orbitals will also delocalize. Once the metal atoms reach an appreciable amount, like that of the metal surfaces within conductors, the energy spacings will become much closer together, and their energy differences will be so small that even the ambient thermal energy of a room temperature can cause the movement of electrons across the energy levels. This, in turn, effectively bands together the electrons into what is known as the valence band and the conduction band, in which electrons can easily move across. Because the energy overlap that occurs in metals between the valence and conduction bands, valence electrons will often move into the conduction band, leaving a vacant hole known as a positive charge carrier in the valence band, with the electrons that promote to the conduction band acting as the negative charge carrier. The charge is then able to flow through the atoms by moving across the atoms within the metal, allowing for a flow of current. Due to these unique properties, metal are the ideal conductors. Semiconductors and insulators, however, are composed of an elemental matrix that covalently bind. This effectively means that for every bonding orbital, an anti-bonding orbital is also present with a significant enough difference of energy that no longer allows for the easy promotion of electrons from the valent to the conduction band to occur at ambient room temperature. This separation of energy is referred to as the band gap energy. If the band gap energy barrier becomes too large, very little to no overlap between the valence and conduction band would be possible, effectively preventing any conduction from occurring, as seen with the insulators. So, pure semiconductors such as silicon-based conductors aren't very efficient. In fact, very little to no electrons are promoted to conduction band at ambient temperature, and such are they're termed as the intrinsic semiconductors. So, how can we increase the efficiency? This can be done by using what is known as dopants. Dopants are atoms within group 3A and 5A of the periodic table, classified as P and N-type dopants respectively. By introducing these atoms into the semiconductor, they become what is known as an intrinsic semiconductor. Dopants can effectively increase the conduction of these semiconductors, allowing the promotion of electrons between the valence and conduction band to occur more effectively. This is possibly due to the relative energy levels, and this is due to the relative energy levels in respect to the valence and conduction bands, where N-type dopants are closer to that of the valence band, while P-type are closer to in energy to the conduction band. Like metals, these dopants are partially filled at their valence orbital and delocalized with the metal of the semiconductor, effectively lowering the energy spacing between the valence and conduction bands. N-type dopants typically contain an extra electron to behave as a negative charge carrier, while the P-type dopants have one less electron that serve as a positive charge carrier, effectively increasing the conduction that occurs between the two bands. In the presence of a junction point where both N and P-type dopants are present, the band gap energy is at its minimum, known as the active band gap. When a voltage is applied, potential energy is supplied to the valence band, which allows for sufficient potential energy that would promote the electrons across the active band gap energy barrier and excite into the conduction band. Once the excitation occurs, the electrons will then want to recombine and return to the valence band to fill that hole that was left behind. During this process, photorelaxation occurs, leading to the emission of a photon characteristic to the energy of the active band gap. Because the band gap energy is too high for an N or P-type dopant alone to overcome the energy barrier, no emission would be seen for these types of semiconductors. So that leads us to the goal of our experiment. The objective is to not only determine the bandgap energies of the intrinsic and active semiconductors, but to also assess its dependence on temperature and analyze how its atomic makeup of the respective dopants contribute to the active bandgap energies. So how can their dependency on temperature be assessed? Well, Boltzmann model for electron population distribution, where E.g. is the intrinsic bandgap energy, K is the Boltzmann constant, T is temperature, shows that within an ideal semiconductor, the ratio between the conduction band and the valence band population should be equal to that of 1/3 at room temperature. This will be further explored with experimental data showing the relationship between applied voltage and temperature used to determine the intrinsic bandgap energies of a silicon semiconductor, as well as 5 different LED diodes. To assess the active bandgap energies and the atomic makeup of different dopants, absorption spectroscopy will be used on only the 5 different LED diodes, as silicon semiconductor is unable to emit light and is primarily used only as a control for the intrinsic bandgap energy experimentation. The formula of dopants shown here can be used to determine the chemical makeup for the respective LED diodes. So my hypotheses include my first one, which is the active bandgap energy should decrease as a function of the increased gallium content, as we can see that in both the blue and green and the yellow, orange, and red diodes, that they both have this dependence on gallium. My other hypothesis is that the emission of blue light will require greater active bandgap energy than that of the red light, just as a function of the wavelength associated with blue being a higher energy than that of red. So, as previously stated, intrinsic bandgap energies will be experimentally determined for the silicon semiconductor, as well as 5 LED diodes using a relationship between voltage and temperature. A voltmeter will be connected to the different semiconductors and placed into a tube alongside a temperature probe. That tube is then sealed with cotton and placed in a water bath that is heated using a hot plate, and the temperature is equilibrated using a stir bar. The voltage is then recorded in respect to the temperature against the inverse of temperature, which will allow us to determine the intrinsic bandgap energy later. The absorption spectroscopy will be done by applying a voltage to 5 LED diodes. Upon emission of a photon, a fiber optic cable is used to detect the incoming radiation, effectively allowing for the formation of an absorption spectra against the wavelength. The wavelength of max absorption can then be used to determine the energy of the active bandgap. So here we have the resulting figures following the intrinsic bandgap energy experiment. After some linear regression analysis, a line of best fit equation is capable of directly showing the intrinsic bandgap energy of each semiconductor. Essentially, by plotting voltage over temperature against the inverse of temperature, you're effectively canceling out this T term you're seeing here, and you're isolating the energy of the voltage applied, which is related to the energy of the intrinsic bandgap energy, as well as this constant C over T. Now, this constant C can be negligible, as it is not considered important in determining the intrinsic bandgap energy. So, as previously stated, simply by recording the slope of each linear regression analysis, we are able to tabulate the intrinsic bandgap energies of each semiconductor, summarized in the table shown here. It is interesting to note here that the pure silicon semiconductor's intrinsic bandgap energy is noticeably greater to those of the semiconductors that contain a dopant, something we expected based on the effects of dopant on the conduction of semiconductors. We can now also assess whether or not the silicon semiconductor is an effective conductor based on the Boltzmann model. As previously discussed, an ideal semiconductor would have a conduction to valence band population ratio equal to that of 1/3 at room temperature. Using the experimentally determined intrinsic bandgap energy, a calculation can be performed to see if this equality is present. And it's very clear to see that this ratio suggested very little to no electrons are present within the valence band at within the conduction band at room temperature. A derivation of this equation can then be done to see exactly at which temperature would this ideal ratio be present. It was seen that the temperature required would be 5.36 times 10 to the 4th Kelvin, something that's simply not practical and therefore proves that pure silicon is simply a poor conductor overall. So, as previously stated, to assess the active bandgap energies and the atomic makeup of different dopants, absorption spectroscopy was taken on the 5 different LED diodes seen here within this figure, whose absorptions were normalized to 1. We can see that the LEDs we used were a blue LED, a green LED, yellow LED, an orange LED, and a red LED, each tabulated with their wavelength of max absorption and their half height width of their peaks. So, to determine the active bandgap energies, a relationship was used between the energy and the wavelength of max absorption. Since the photon emitted during the recombination between the valence and conduction bands at the junction point is characteristic of the active bandgap energy, no further calculations were necessary. Sample calculation for the active bandgap energy for the blue LED is shown here. This table shows a summary of the wavelength of max absorption, the experimentally determined active bandgap energies, and the half height width of the absorption peaks for each diode. The half height width was determined by subtracting the wavelength of absorption at half height on the low energy tail of the peak from the wavelength of absorption of the half height on the high energy tail of the peak. A clear trend is seen here that the photon energy emitted by the respective LED diode trends with the energy of the wavelength associated with the respective wavelength of visible light. So blue, high energy wavelength, and we're seeing a high energy for the active bandgap. Red, low energy wavelength, low energy active bandgap. So to recall, P and N-type dopants are composed of the 3A and 5A grouped atoms on the periodic table respectively. The scope of this experiment was to analyze the molecular formula of the P-type dopants present within the LED diodes, specifically the elements of aluminum, gallium, and indium. To do this, some algebra was required. A quadratic relationship exists between the active bandgap energies and the ratio of indium to gallium for the blue and green diodes, such that the ratio can be algebraically determined using the quadratic formula. These ratios are tabulated within the table here. The relationship between aluminum and gallium within the yellow, orange, and red diodes were then determined using a linear relationship with their respective bandgap energies seen in the table here. To better interpret these results, we can plot the active bandgap energies against their respective P-type dopant ratios. After regression analysis, we can see that both show a significant correlation between their energies and the ratio of metals, which means there's a direct connection between the two. It is seen that in the blue and green LED diodes, increasing the concentration of indium will effectively lower the active bandgap energy for the semiconductor. In the red, orange, and yellow LED diodes, it is seen that increasing the concentration of aluminum will effectively increase the active bandgap energies for the semiconductor. So now let's just recap and reflect and look at some concluding results here. So the silicon diodes are poor semiconductors. That seemed pretty clear in our experimentation earlier. We also saw that lower active band gaps correspond to higher wavelengths of emission. We also see that an increase in the indium to gallium ratio decreases the active bandgap energy, while the increase in aluminum to gallium ratio increases the active bandgap. So now let's take a look at how our hypotheses hold up at the end of this experiment. So in our first hypothesis, we saw that the bandgap energy seemed to be more relevant to the total molecular makeup rather than just the gallium, as we saw that there was this important relationship to both indium for the blue and green and the aluminum for the red, orange, and yellow. Our second hypothesis showed that the blue light did exhibit a higher active bandgap energy than that of the red light. So that was consistent with our expectations. Thank you for your attention. And I just want to give you a thank you to this department, and thank you to the guidance of Dr. Wagner and the TAs of this lab. Thank you.